Professor Kulik is a professor in the Department of Chemical Engineering and Chemistry at MIT, and she received a PhD from the Department of Material Science and Engineering at MIT also in 2009. And then she did her postdoc at Livermore and Stanford. And then she joined MIT as a faculty member, and her research group uses computational chemistry and machine learning for material discovery. Her research has been recognized by many awards, including the Office of Naval Research Young Investigator Award, the NSF Early Career Award, and also the American AQ Computational and Molecular Simulation Engineering Volume Impact Award, and Hans Fischer Senior Fellowship from the Technical University of Munich, and also many other awards. And without any further ado, I'd like to welcome Professor Kulik.
Thanks for the kind introduction, and trying to hide as many extra Zoom widgets as I possibly can. So today I have the pleasure of telling you a little bit about my group's work. I'm a computational chemist, as you heard, and how we've integrated machine learning into what we've done. But I felt a little bit of extra pressure in thinking about putting together this talk because this is actually the third time I've spoken at Berkeley. The first time was in chemical engineering. The second time was an inorganic chemistry seminar, and that was only 2 years ago. So I had a quick panic. I wanted to look at my slides and make sure that there wasn't a lot of overlap. I don't see a ton of familiar faces, but I can assure you that most of what I'll be talking about today, we had not done 2 years ago. And just to kind of reiterate that point is that if you're not at all familiar with what my group does, we do a lot of machine learning, open shelf transition metal chemistry, and transition metal complexes and metal organic frameworks. And if I were giving this talk approximately 2 years ago, I'd probably have told you about some of the feature engineering work we did to predict spin state dependent properties of transition metal complexes early on. We just got into machine learning for transition metal complexes back in about 2016. And early on, we paired these models with evolutionary algorithms to try to optimize materials for, say, phenomena such as spin crossover. And we got really interested in uncertainty quantification in neural networks. And so we spent some time looking at properties of the latent space for uncertainty quantification. This led us down the path of doing efficient global optimization with 2D expected improvement and using neural nets rather than Gaussian processes, which were more common at the time. And so this allowed us to achieve about 500 to 1,000-fold speed up in materials discovery. To put that in context, that corresponded to about design rules in weeks instead of decades through random search for redox flow batteries. One of the works I'm particularly proud of, we paired this type of evolutionary optimization approach with method uncertainty. So we're accelerating computational predictions with surrogate models, but we actually incorporated the fact that different density functionals will give you different results. And we looked for consensus among density functionals to show that we had robustness in our computational predictions. We also detected what's called multi-reference character and avoided regions of high multi-reference character all in the optimization. Then moving on from chromophores and redox couples, we went into something we thought was a little harder, which was catalysis. And we optimized in spaces of 16 million catalysts, again, using surrogate models. And then around 2020, we started getting into machine learning for metal organic frameworks, first trying to understand the mismatch between hypothetical materials that people can come up with and what's already been synthesized experimentally. And then this led us down the path of trying to leverage all of that experimental literature data to predict measures of metal organic framework stability directly from the literature. And then use those models to then identify, circling around, how you could identify stable materials that would make good MOF catalysts. And we're not the only people who work in the area of machine learning and high throughput screening for transition metal complexes or MOFs. Here are just a few names here. But the reason I put all of this on one slide is not because I'm trying to give a 3-minute talk, but because I want to talk to you about what comes after doing all of this. And so usually when I would give a talk that focused on this type of thing, I would get a number of different questions, get many different types of questions. But today I'd like to first review some of the most common questions you get when you give a talk like this, and then give you some of what I've started to believe have been our answers to some of those questions. The first question I would get is, you're searching these large spaces. Has anyone made anything that you've made a prediction? What about experimental validation? And then the next question I would very frequently get is, what about an ML prediction that actually surprises me? I'm an expert chemist, I could have predicted for you what your ML model came up with. What is a prediction that's actually surprising? And then, I would get a lot of questions in the general area of about, what about realistic conditions in the lab? What about a real transition mount complex that's in solution, in mixtures, and so on. And then I'll come back to this, a lot of times we and others sidestep explicitly computing transition states. So how do you predict reactivity? How do you actually tackle predicting transition states? Anyone who's computed a transition state knows that they're quite computationally demanding to do it. And then I don't know if I'll get to this, but a very frequent refrain I get, and I feel like if I come to Berkeley, I have to talk about DFT at least a little, which is, what about the fact that DFT isn't? So I'd like to tell you a little bit about some of our attempts to answer some of these questions. And so to tell you about the first two questions, I have to introduce you to something that you may or may not be familiar with. I tend to assume people are not familiar with it, and that's the field of polymer mechanochemistry. And so just bear with me if you're a world expert on polymer mechanochemistry, I apologize. So I certainly was not coming into this. My interest was transitional complexes. And polymer mechanochemistry is a very exciting field, but all of the advances in this area are very synthetically complex, characterizations complex, and so it takes a lot of time to make observations. And so in particular, Jeremiah Johnson, Steve Craig, and co-workers in the science paper in 2023 showed something really exciting, which is kind of intuitive in retrospect, but was a really exciting observation, which is that when you have polymer networks and you link them up with weak, what are called mechanophores, which are molecules that selectively and easily break under force, you actually make stronger, macroscopically stronger networks. And so you do that by dissipating force and dissipating tension. And most of the time, mechanophores are organic molecules. So I joined a center that Steve Craig leads called the Center for Chemical Innovation, the Monet Center. And I noticed that around the same time, Steve Craig published this paper in Nature Chemistry, which again was a very laborious multi-year process where they were starting to move into characterizing transition metal mechanophores, and ferrocene had this very interesting behavior where, depending on how the cyclopentadienyl rings of ferrocene were covalently attached to each other, if they were, then you would get this peeling motion of the ferrocene, and this would be lower force. Whereas if you had unlinked cyclopentadienes, then they would shear apart, and this would take higher force. And so what we would want to be able to do is design something that has this kind of chemistry, because the top thing is what we can incorporate into a polymer network. But we want this type of mechanism. We want, say, something like a low force peeling mechanism that we can incorporate into a polymer network. So we wanted to look at how could we go about computationally designing these types of systems. I just want to emphasize that each of these insights, the characterization of the breaking force and things like that, require a lot of time and manual experiments. But the other reason we're so excited about this is because it allowed us to sidestep the question of synthesizability, at least to start. And that's because if you go into the Cambridge Structural Database, which is a repository of many crystal structures of experimentally synthesized and characterized materials, you'll find out that there are about 15,000 metallocenes that have all been synthesized, characterized, have their synthesis recipe in the literature, have their structures well defined. After you get rid of you only account for ones that have the same molecular graph, you end up with about 5,400. Almost all of them turn out to be ferrocene, so we stuck with ferrocene. We could have looked at other metals. And once we're going to do these types of mimicking force experiments, what we're going to do is we're going to attach polymers in different points on the ferrocene. And the result is that after regiochemistry, we end up with about 12,000 combinations. And so we did not do calculations on all 12,000 of these ferrocene mechanophore polymer combinations, but we took a sample of about 5% of the space. And this particular way we do this is not just standard equilibrium DFT, but it's with something called COGEP. It basically is a cheap way of simulating the effect of force by applying a constrained geometry optimization that can tell you about where bonds will want to break. And we saw something that largely recapitulated what the experiments had shown. So the green are what we want. Those are the ones where the cyclopentadienyl rings aren't covalently linked. And it's much easier to get low force compounds if they are covalently linked to each other. But we see this really long tail here. So there are lots of opportunities to lower the force, and we're going to sort of draw a line here and say anything below 3,500 piconewtons is a relatively low force cleavage, and anything above we're going to call fairly high. And then we're going to train a pretty cheap and dirty multi-layer perceptron classifier. And a couple of things we're doing here. We're training them on graph representations, racks that I showed you on the first slide. And so they know nothing about through space interactions, but they're really cheap to obtain before we do any complicated calculations. So we can screen large spaces, and it does a pretty good job of distinguishing low force versus high force compounds. And then we use that model to predict which new compounds should we go back and do DFT on. And indeed, we're able to strengthen the lower tail of lower force compounds. And so there's some things in here, to first not answer question 2, what are the things we expected? What did the expert chemists, because we were working with Steve Craig at Duke, and we were working with people who know a decent amount of chemistry, what we expected beforehand were some of the things we saw. So we thought, pi-pi stacking or a strong hydrogen bond that can mimic the effect of a true covalent link if it's strong enough. And that's indeed what you see in a fair number of these. But there were other things that were surprising. Now, unlike the active learning campaigns I showed you on the first slide, we stopped at this point because when we retrained the MLP on the data set that I'm showing you here, and we rescreened the space, there were only about 100 compounds predicted to be low force. And so we decided it was exhausted and that was really enough. So the second thing that was maybe a little bit unsatisfying about this is that there's no knowledge of through space interactions in our models. And so you might want to know, okay, what about 3D geometry? And so in particular, the dihedral angle of the points on which you pull on plays a really large role. So if the dihedral is 0, if the handles are aligned, and then you do enforce this peeling mechanism and get lower force. So that's something interesting, but not too surprising. We can also train regression models using features like this. And we also introduced a sterics non-covalent interaction feature, which you would only get after doing DFT calculations. And the regression model does a little bit better than our classifier did. The newly retrained classifier and regression models that have information now about both the dihedral as well as how strong is the non-covalent interaction between the two rings, they now weight pretty heavily in the feature importance. They are about 1/3 of the features, but this highlights why we were able to do this with just the graph-based descriptors. So now I want to get to the question of what was actually surprising. And that the thing that surprised us, because in practice, it takes the experimental team about a year to synthesize and characterize just one of these mechanisms. Maybe some will go faster, some will take longer, but these are really difficult experiments. So if you think about 5,000 or so different samples, that's not something that you could ever do in your lifetime, not even one lifetime. And so what was surprising? Like, what would they have not have looked at? And this was the surprising effect we found, which was that steric bulk around the cyclopentadienyl ring lowers the force for cleavage. And what you're looking at here now is something called EFEI calculations. And the way to interpret them is that where these lines cross this horizontal bar is where the molecule would be expected to break apart in a single molecule force spectroscopy experiment. And in particular, the one that we picked out, so I'm showing here also the control, which is just plain ferrocene, that's the gray dashed line. The one we picked out has the CST ref code NUSSEG, and it is able to lower the force quite substantively. It has a TMS group on the cyclopentadienyl ring as well as a carbonyl. And the experimentalists looked at it, and yes, this is something someone synthesizes in CSD, but they have to not just be able to synthesize it, they also have to be able to do ROMP in order to incorporate it into the polymer strand and then be able to incorporate it into polymer network. So it's a little more complicated. And so they were like, can you get rid of that carbonyl? And we said, sure. So you end up with just the red line MTMS. And so you see, we still do pretty well. And what we hypothesized based on looking at the electronic structure was that electron density from the TMS group was actually being directed into the ring. And the result was that when you have this heterolytic cleavage of the cyclopentadienyl ring away from the iron, that you're actually stabilizing the transition state in the case of MTMS versus the ground state, because it's now more favorable for the iron to lose the cyclopentadienyl ring. And so what we hypothesize is you just move this to the ortho position and this effect will go away. And indeed, that's what you see. If you move it to the ortho position, you lose the mechanism of transition state stabilization, and you go back to the control of just standard ferrocene. So from this observation, this is the one that we asked the experimentals to make. So from about 5,000 candidates, we asked them to make just one, and it was this ferrocene with the TMS group added. And the answer is, I think very highly of Steve Craig, but he has insisted to me this is not something that he would have ever have thought of as a potential mechanism to explore. And so the first thing they do is they just do the single strand experiment. And so what we should expect with just the single strand is the single strand should break faster and the polymer network should break slower. And so in comparison to ferrocene, which is P1, MTMS ferrocene P2 does in fact, what this line is showing, does in fact break faster. And then this is the polymer network. So the polymer network, we're able to tear it, strain it 4 times further than control and twice as far as standard ferrocene when we incorporate MTMS ferrocene into the polymer network. But and again, we never did polymer scale predictions. We did everything at the molecular scale, and we were able to achieve this 4-fold increase in network toughness. But my absolute favorite thing about this, as a quantum chemist who always works just with scaled atoms, is that this is something you can actually see with the naked eye. So all 3 materials will tear. The control tears first, it's already teared. The one with ferrocene tears next, and then our design polymer tears last. And it's just the video that corresponds to this experiment I showed you on the left. And so, I think it's just my job as admittedly a domain scientist working at the interface of ML and chemistry to be able to make these types of exceptional predictions where we defy chemical intuition, in a way that's even faster. This is still hard, but to think about making this even easier and accessible and think about how do we do this in more material spaces that remain hard and resist automation, I think it is a key priority area. So I'm going to switch gears now, and I'm going to tell you a story that was inspired by a collaboration I had with a company. So a company came to me, I still have this collaboration, and maybe I will do my best to not name the company because I don't want to shame them. And it's been a fruitful collaboration, right? But they came to me beforehand and they said, we're going to give you this data set and it's going to have experimental results of around 5,000 reactions. And I was like, this is great. I can do all this machine learning on this experimental data. And they're like, and if you make new predictions, we'll make new catalysts and this, and I'm like, this is awesome. Then I actually saw the data. And so probably if you have more experience with synthesis than I do, you would have known a couple of things to expect. So one is that all these were done kind of one-pot syntheses where they took a pre-catalyst and a ligand, and they mixed it together. And the only thing they recorded for us at different conditions, there are more complexities. I won't throw them completely under the bus, but they basically told us, did the reaction work? Yes or no. It was a polymerization reaction, and the answer is yes or no. There are other issues with data labeling to do with, depending on the conditions you run things at, your answer can change from yes to no or vice versa. But this actually inspired us to think a lot about, real world conditions, which is that maybe a lot of times you don't know what is actually the species doing the reaction. And we're still working on this. I won't say that we've finished it, but we've tried to start to understand how do you actually predict, what are the best ways to use data-driven models to predict what complex will form when you have these different types of combinations. And the first thing we did, so I'm going to tell you a couple stories related to this. The first thing we did was just to take all the ligands again from the CST. And the first time we did this, I'm going to be telling you about the second time. The first time we did this, we required every time the ligand appeared in the CST that it only binds to a metal, regardless of the metal identity, it only binds in a single pose. And so we're calling this non-hemolabile. And so when you get to this, you get to a data set of around 70,000 ligands that bind a single metal in a single pose, and can be easily parsed and are valid structures. And a fair number of them are, and I will, if there's any real chemists in the room, I don't actually know if there are, I will apologize in advance. I'm going to refer to something that's really a mixture of denticity and hapticity. I'm just going to refer to it as coordination number, because we're talking about predicting points on a molecular graph in terms of how many times a ligand coordinates a metal. Our code in the back end and in the interface can have its coordination number prediction mapped directly to a definition of denticity and hapticity later. But for the sake of our machine learning task, we're just trying to predict how many atoms on a ligand bind to a metal. So for instance, this is a 6 coordinate in our lambda. And so most of them are bidentate or tridentate. But you see we have a decent amount of data here. Most of them are dictated, are pushed towards CN or O. Interestingly, there's a decent chunk that coordinate the metal to carbon. There's almost no silicon, which I'll come back to in a moment, and there's a little bit of phosphorus and sulfur, and the metal distribution is pretty wide. So we don't have huge counts in any one given metal, so the models are not going to be metal specific. I often get questions about that, but we have good coverage of the periodic table. And you can pretty straightforwardly train a GNN to predict first the coordination number. Is the ligand going to be bidentate, tridentate, and so on? And when the model is wrong, it's usually wrong by 1. So it's learning good trends. So here's a good example. The correct answer for this ligand is that both oxygens of the carboxylate coordinate the metal, but the model predicts only 1. Which is a pretty convincing failure mode, because there's plenty of cases where carboxylate might find only once. This has all 4 nitrogens here and the sulfur coordinate the metal. The model only predicted 4. We don't know which 4, but this is partly because there's fewer high density ligands in our data set. And so bidentate for sure is where it's most accurate, and overall accuracy is about 88%, AUC is about 98%, and precision and recall are not bad. But what we actually want to do is be able to put this in an end-to-end pipeline with my group's most simplified code, so we can actually predict coordination and then generate the structures. And so what we want to actually be able to do is predict which atoms coordinate the metal. And if you just think about this from a combinatorial perspective, the accuracy is going to be really high, but there's going to be, the answer is almost always no. So there's a lot more no's to predict, and so the accuracy can look trivially high. You can get a 98% accuracy without too much trouble. So positive accuracy is lower than negative accuracy, balanced accuracy is in the middle. But we're going to define a more stringent requirement, which we call molecular accuracy, which is getting every yes or no prediction right for a ligand. So exactly predicting the coordinating atoms. And there we drop to about 85% in this initial model. And here's an example of something we get wrong that is not molecularly accurate. So the correct answer is this nitrogen, this oxygen, and this nitrogen coordinate. But the model chooses this nitrogen that's nearby. So again, when the model is wrong, it's predicting pretty plausible structures. And you might ask, do we have to go through the trouble of doing all of this? Maybe simple heuristics would just work. And so we can throw out the carbons and we can say, anytime we see a heteroatom, like maybe that heteroatom will bind to a metal. And then if you do that, you get a baseline accuracy of 22%. If you're curious, I've also done this with GPT, but I did it with GPT-4. I didn't do it with GPT-5. GPT-4 was terrible, and I took it out of my talk because I want to have time to update. It basically, when it was doing reasoning in 4, it basically was doing this heteroatom counting and was achieving accuracy. I think peak accuracy I got from GPT at the time was actually having GPT train a random forest model. And the random forest model got about 60%. So this is some examples of what the model can do. So here's an example. I'm not a great chemist, so I wouldn't be able to tell you off the bat which atoms are coordinating and not coordinating. This is a tridentate pincer, and those are the correct coordinating atoms. It captures well high denticity, that this should be tetradentate. It captures hapticity, so it doesn't explicitly get told what hapticity is, but it detects it. And even though we don't have a ton of cases where silicon is in the data set, it does a good job of predicting that this is a silicon ligand that coordinates the metal when you have much more common nitrogen or phosphorus nearby. So we wanted to, why do I have a coordination number model in the first place? Well, we wanted to use them synergistically. And so the coordination number model predicts a binary classification, is it bidentate, tridentate, and so on. And for instance, here's a ligand where the coordination number model is pretty confident that this ligand is bidentate. So it has a 0.79 probability of being bidentate. The coordinating atoms model is less confident. It predicts that this phosphorus has high confidence of being coordinating, but it predicts this sulfur to be just below the boundary of coordination. So it predicts with low confidence phosphorus only coordination. And so we have this synergistic approach to enforce chemical consistency between the models. And so what we would do is we would revise this to say that the second one is coordinating because the first bidentate model is confident that it's bidentate. And so we would synergistically update. And when we do this, we raise the overall accuracy, molecular accuracy of our coordinating atoms model to about 88%. So either model can override each other, and I'm about to introduce a third model. And this is something that I talked about the very first models of this in my talk 2 years ago at Berkeley, but I'm going to tell you about what we've done since. And that's the very interesting fact that thousands of ligands are hemilabile. You might have seen that I threw them out in the first study we did. And we had built a model that handled class 1 hemilability in kind of a rudimentary way. So as far as I know, these are our definitions of hemilability. So bear with me if someone knows a different set of definitions. The first is the most obvious, which is that you break one bond between the two cases. And so one has fewer bonds, but otherwise the coordinating atoms are a subset of each other. The next would be you go and you change the denticity, but you also change which atoms are coordinating at the same time. The next would be you keep the number of coordinating atoms the same, but their identity changes and is shared between like at least one atom overlaps. And the last would be like say thiocyanate and isothiocyanate, where the coordinating number stays the same, but the coordinating atoms are not shared at all. So we previously had a model that predicted class 1 hemilability. And I'd say the main thing that we did that was really creative in this work was we used semi-supervised learning with label spreading. And that's the fact that you have ligands deposited in the CSD, and they may be deposited only one time. And just because they've been deposited one or a few times only in one pose does not mean in solution they will never be hemilabile. So what we did instead was we took a set that were really frequently observed in the CSD with multiple different metals that are known to prefer different coordination types. So taking late transition metals and mid-row transition metals, and we took them as a small set, that's what's called small here. And then we used label spreading to find the most similar ones to those to then enlarge our set. And the main thing we observed was that if we did a random split of the data, then we had much lower performance than the small set that was about an order of magnitude smaller. And then we got the best performance after we used the semi-supervised learning. But this was an XGBoost model, and it required you to assign beforehand what were the two modes that you're moving between, and it only worked for class 1. The main thing that was a takeaway from this was that we got some, a lot of times people focus on the donor atoms and how that can influence hemilability. And the reason you want to do this is because you can control catalysts and do all sorts of nice switchable functionality if your ligands are hemilabile. What we found was that the global structure, everything 3, 4, or more atoms away from the metal coordinating atoms, were the most important for predicting this hemilability, which again was another case where we had some surprising design principles. So this time we went back and we took our GNN, and the first time we trained our GNN to predict hemilability, it wasn't doing that great. So it wasn't outperforming these XGBoost models. And you can see here, even our fine-tuned model, because it's more general, because it predicts all 4 classes in a general way, it's still, you know, not significantly, it's basically on par with the XGBoost model. But what we did to help improve accuracy from the baseline model, because we only have a relatively small set from a GNN perspective, we only had about 5,000 points or 10,000 points, was we took for granted that the original models, which had never seen these ligands before, both for physical and for numerical reasons, would be more uncertain on hemilabile ligands. So because the hemilabile ligands were not in the training data, when we predict coordinating atoms, that model should be uncertain about what the coordinating atoms are of a hemilabile ligand. It also should be uncertain because the answer should be multiple possible answers. And so actually now the fine-tuned model takes as input the coordinating atom uncertainties from the other model, and as a result, it does a lot better. So here are examples that are improved with fine-tuning. So here's a non-hemilabile ligand that was incorrectly predicted with the default model to be hemilabile, but the correct model corrects it. Here's an example where the model thought it wasn't hemilabile. It is this class 4 type of hemilability, and the fine-tuned prediction correctly predicts it. In case you're wondering, like, what is the drift with the fine-tuned coordinate prediction probability, the model is still most uncertain on the ones it's incorrect on. So the fine-tuned prediction probabilities are a meaningful way of UQ on the model. But here's an example of something we don't fix. It's not all roses. So this looks a lot like turkey, which I'm showing over there. But now we have 2 carbonyls. And because we have these 2 carbonyls, there's less flexibility in this ligand that makes it not able to do this class 1 type of hemilability that turkey does. But the model's mostly seeing things that look like turkey. And so the fine-tuned model gets closer. It's more uncertain than the default model, but it's still on the side of wrong, right? So how do we put this all together for end-to-end structure prediction? Well, we take an ensemble approach. So first we predict the coordinating number and coordinating atoms. We use those as inputs to the hemilability model. We predict hemilability. If it's not hemilabile, then we just return one prediction that allows you to build the structure. If it is hemilabile, then we enumerate through likely possible combinations of all the different hemilabile poses and return the highest probability ones. And so this allows you now to go from just the SMILE string of a ligand to 3D structure. And we've also recently improved structure generation significantly in MolSimplify, and that paper is forthcoming with the journal any day now, but the code is already live. So how do we validate these different poses we predict? So what we're going to do is we're going to try to get energies from DFT. And first, we're going to take known instances of hemilability observed in the CSV. So the same ligand and metal in 2 different poses. And that's what I'm showing at the top here. And those poses are usually pretty close in energy. And then the ones that we predict to be hemilabile, their average energy is pretty close to the CSV value, whereas the ones we predict to be non-hemilabile, then the energy is much higher for these alternate poses. So that's the closest we've been able to get to validation. This is, again, like a hard thing to do just with DFT. But just to show where this is useful for things, this is a collaboration we've had with Teresa Gordon and Leo from her lab. And Teresa's been advancing language models for generative design of transition metal complexes. And there's lots of ways you can assess the SMILE strings that come out. But one of the ways that we added to this project was we applied our pidentate models, the coordinating atom and hemilability models, to see is the coordinating atom identities chosen by the model feasible. And so you can see the plausibility of both the language model from scratch and the prompt engineered TMC llama model. In both cases, the plausibility is very high. We're basically at the level of where the model itself is, you know, our pidentate model's accuracy is. So you might ask, well, what about other things that already came before that? And so there's only a few generative models in the space of transition-mel complexes, but these models are all outperforming the ones that we could actually make comparison against. So if you look at this variational autoencoder from David Bell-Cells, we only get about 65% agreement in coordinating atoms. So this is pretty good. So I'm running short on time and I wanted to get to transition states. So I will maybe skip through some of this. But I will make a brief mention of it. One of the things we want to do is not just be able to predict novel structures or how metals and ligands bind, but we want to have a better understanding of the mapping between a ligand or a complex and what it is used for. And so what we wanted to do was take cases where structures were well defined and then annotate them with their application. And for instance, it's very easy to train models on the language and abstracts and titles to be able to predict what is a catalyst and what isn't. And it's trivial because the word catalyst is often in there, but you can look at what words show up with these types of models. If you throw them away, and you can get about 89% accuracy of knowing if a paper is about catalysis or not with fairly light models. And so then we can start to ask ourselves if we can faithfully annotate which structures are associated with catalysis and which not, you know, what do we see that's different about a transition-mel complex that's a catalyst versus one that's not? And so it's surprising some metals are enriched while others aren't. You might see some earth-abundant metals here are actually not that frequently showing up relative to other applications. And the other thing that surprised us at first, but not in retrospect, is that the catalyst versus the non-catalyst, there's not a ton of descriptors and features that are that different. And that's because what's in the CSD is primarily pre-catalysts. And so the result is there's only a slight shift, let's say in coordination geometry, that say there's more octahedral transition-mel complexes that are not catalysts than those that are. And so we use a Bertopic model on the TF-IDF vector to assign other types of application spaces, bioimaging, photocatalysis and just photophysical applications and spin crossover. And we're currently in the process of doing this. You could only belong to one category in our original incarnation. Now we're doing overlap categories. And this is the UMAP of the different text embeddings. And this is showing how, for instance, the catalysts all live over here and the other applications live further away. But you can dig down further into subcategories of catalysis and see, for instance, that the chiral catalysts are very distinct from the ones for polymerization, whereas polymerization and metathesis sit very close to each other. So this seems like it's giving a reasonable estimation based on our intuition of where things belong. But then you can now relate this back to structures, and you can see which structures are enriched in each of these different types of sets, and that there's certain types of structures that appear in all of the sets. For instance, this nickel salin type motif shows up in basically everything. Whereas other types like linear gold complexes are really common in catalysis, but not in other application spaces. And so what we did was we took any common structural motif that was really common as signature of spin crossover or catalysis, and then we enriched the ones we've been able to label based on their use case with substructure matching to create subsets. And so this is all based on the TMQ data set, but what we've done is we've now basically divided up TMQM into subsets based on their application space. In version 2, we do this more at the ligand level. So as promised, I wanted to get to a little bit of something that we've done very recently on transition states. And the other thing that the reason I'm showing this again is that when I showed this thing here where I said we optimized 16 in a space of 16 million catalysts, the two things on my X and Y axis are just reaction energies. They're not activation energies. And this has been a chief limitation of anything those of us interested in catalyst optimization have wanted to do. And so one thought is to try to take something like the transition 1X data set and be able to rapidly use it to use generative models to generate transition states. And this was work done by Chen Yuan, whose picture I think is on the next slide. And with these types of models, what you can do is you can generate structures once you take into account the equivariance you should have for the reactants and products with respect to each other. And you can achieve prediction of transition state structures to within about 0.1 angstrom or less of the true transition state structure according to DFT. And this allows you, when you do a single point energy, to get activation energies within a few kilocalories per mole. So we're approaching chemical accuracy. You can do this the first way we did this was all stochastic. So you would do 40 samples and take the best of 40 samples and use a fair amount of compute time to do that. You can do this deterministically with optimal transport, and it's a lot faster. And you also get just as good or better performance. Now, there are cases where you can end up with relatively high errors on the energies and relatively low errors on the structures or vice versa. So it's not guaranteed that just getting a good transition state gas gets you to the true transition state faster. But the key point here is that with React-OT, the second model, the inference time comes down quite a bit. And in particular, Chenru worked a lot in my lab on these types of recommender strategies of determining when is the ML model confident enough and when should you do the DFT calculation. And that's what that green bar is showing here. So React-OT was able to now achieve 0.1 angstrom mean RMSD, 0.05 angstrom median RMSD, all on transition 1x data at a much lower inference. So that's the starting point of that. What I want to tell you about now is what we did next, which is work that Samir Darowich did. He came to me from Matthias Niefert and Johannes Tassner in Stuttgart. And we wanted to know, or one of the things that's always been bothering me is that these models are suspiciously good, right? So they can predict the structure of transition state, but can we actually use them for catalysis? And so what Samir and I were really curious about was how do you show that these models can generalize? And it's really expensive to go and recompute transition 1x at a high fidelity DFT level, at least I don't have Meta's computers. And so what we did was we tried to design what we call a couple of new data sets. The first one is that I'm going to tell you about is transition 1x TMCs. And so what we did was we looked for all of the ones that were predicted by pidentate to bind monodentate to a metal. So we could insert a metal complex into our reaction that already existed. And so then we looked through the CSD and we found the smallest conceivable transition metal complex. The first time I wanted to do this, I wanted to do bare metals. That doesn't work, by the way. So what we did was we picked these 10 metals that you're seeing here, and we looked for what is the smallest, most common thing that is the small, and most of the time it was like titanium with chloride. Sometimes it's with cyanide and things like that. And we recomputed all this at the GFN level. We did PRFO and IRCs. And this is what the data set looks like. It's about 36,000 new reactions. And so the vanilla React-OT fails miserably, like catastrophically badly on this. And so you end up with activation energies that are wrong by thousands of kilocalories per mole. You end up with high RMSDs. What we did instead so I didn't talk at all about transition 1x swap. That's just 2p versus 3p elements. You can fine tune the model. So once the model's seen a little bit of this data, 25% of the data, it does pretty well. It's still doing worse than, say, the ones we had on organics, but everything is worse when a transition metal is involved. That's probably what they'll write on my tombstone. Yeah, so you can get the models down to pretty decent accuracy, especially compared to where vanilla React-OT was starting from. You don't need to do anything exotic with encoding like the elements either. As long as it's seeing the elements, it does a lot better. But that wasn't super satisfying, because what we tried to do next that I'm not going to show is we tried to like bring in a real transitional complex, like what you actually want to study, like something that analyzes hydroformylation, let's say. And the model still performed terribly even after it's seen all this data. So I was like, isn't there an easier way we could do this? We just need the model to learn something about the new ligand chemistry. And so we made fake reactions. I guess Samir likes to call them pseudo reactions. And what we did was we did a CREST conformer search, and we took the lowest energy conformer to be the reactant, the highest to be the product, and the transition state to be the next highest. And when you do this and you add them to the model, you get much more data efficient prediction of high accuracy structures. You don't need to see real transition states to teach the model about the overall ligand structure. It just needs to see some conformational variation. So this turns out to be a very data efficient way to make the generative model generalize better. So I am right at 45 minutes, and so I'm going to completely skip this, I guess, because this is, I think, the only slide pretty much that was in my talk 2 years ago. But I will give a brief like postage stamp level shout out to it. We're really interested in the question of which functionals are accurate enough for transitional chemistry. I don't consider this a solved case. And we really realized that when you go to different parts of chemical space, the right answer changes. So a couple of years ago, we developed something we call the density functional recommender, which uses the electron density as inputs, and then predicts what is the optimal functional to use from about 48 different functionals. It does a really pretty good job. It does better than transfer learning, and it preserves the rank likelihood of different functionals showing up. The main thing you'll notice is that the right functional, first of all, never tops 50%. The right answer is never one particular functional. And that when we move to new out of distribution data, the focus shifts, but the model correctly captures that because it's been trained on electron density. And the thing I wanted to mention is, because this paper was only accepted a couple of days ago, is that one thing you might say is unsatisfactory about that is because you want to know something about the physics, not just like, oh, use M06L on this particular compound. So inspired by some comments from Kieran Burke at one of my talks, we went back and looked at this a different way. We again still trained a Baylor power neural network on the electron density. And what we wanted to do was basically start to turn this into a self-tuning functional, have it take based on the input density and predict out what are the parameters of the functional rather than choosing the functional class. And this is again showing the same thing. And what we're able to do now is predict the optimal amount of part-to-clock exchange in the functional. And it works and it generalizes to the out of distribution compounds. And so generally just sticking with a single family of functional, but allowing only the Hartree-Fock exchange to be tuned. You can imagine doing this for IP tuning, omega tuning, all sorts of things. We get about errors of around 4 to 6% of Hartree-Fock exchange, which corresponds to similar errors to what we got with the recommender, but now we're working in a closed loop system where you can imagine taking the output density, re-inputting it, and having a self-consistent cycle within the framework of ML. Yes, for sure, you can go to equivariant networks. This is not equivariant. With the data set sizes we've seen, we've never seen an actual quantitative benefit of it, but you would expect to, certainly in certain data regimes. And so those are some of the things we're still thinking about, and I think I finished on time by skipping through some things. So if you were asleep for the past 45 minutes, I'd like to tell you what I think I answered a little bit about some of the questions I posed at the beginning. You know, we moved into a new to us area of trying to tune polymer network properties from molecular scale predictions. And we came upon a design principle that I certainly would never come up with, and that the experimentalists, at least to my face, tell me they would never come up with, and I really believe them. And we were able to realize that experimentally. And it's possible now to predict structures of ligands and how they bind metals. I'm still a work in progress, but one of the things that they can be used for is to assess generative models. And this I'm specifically referring to the transition state models. There's a lot of really impressive performance of models that have come out trained on transition 1X, but they're not generalizing outside of the training data. I think we've shown one way that's useful to do low cost data generation to generalize chemistry better. There's also obviously going back to the architecture and other things like that, but I think this could have use in other areas besides the one that I just showed. And I'd just like to finish by acknowledging the students who did the work. So most of the work I told you about in the first part was done by Ilya Kevashvili, a fantastic postdoc, who now has his own lab as of this year at Baylor. And then I moved into telling you a little bit about work done by James Pony, who's a fantastic graduate student currently in my lab, as well as earlier work done by Chenru Duong, who now has a startup called Deep Principle. Some of you may have heard of. I told you about work done by Samir when he was a visiting PhD student. and the collaboration that Jacob, Aaron, and I have had we're very thankful to collaborators, Teresa for bringing us into the generative work, and Steve Craig for bearing with us and doing some synthesis. And I'd be happy to take any questions if there's time.
Great presentation. I think we are actually out of time, but we can have one question. And Dr. Heather will have like 30 minutes after the seminar if you will have a question. But we can take one more question right now.
We played around instead of like getting the kind of pseudo reactions with crust, maybe like using XTB with like neb or something, but also try to retraining eco-dependent cheat.
So we did do that's everything we're doing. That's the full data. Yeah. It's just that the what we've played around with the most is the crest is just a lot cheaper. Even if you did that on DFT evaluation. What we've looked at is whether all of the things we were doing the testing were on XCB quality data. We're looking at whether that perturbed the model's ability that was originally trained on DFT. And what we're also able to show in the preprints is that it doesn't significantly worsen performance on DFT, even though we know the XCB geometries aren't that great. But yeah, what I was showing with the vanilla and the fine tuning is on PRFO and RRC, all at the XCB level.
Thank you. So, you have a question before the statement. I think there is one question over Zoom. Raise the hand over Zoom.
Oh, I didn't see.
I think it
Should be fine.
Okay.
Yeah.
One third.
Okay. Yeah.
But like I'm very flexible. Like if you would like to have a coffee,
Okay.
we can also do that instead of having in my office. Just whatever you.
Yeah. I just haven't eaten. I haven't eaten lunch. That's my lunch. But as soon as I eat it, I was gonna come over to your office. But whatever you want to do.
Okay. Meet up in
Yeah.
your office.
Did I unmute you, John?
Yes, you did. Thanks. I can't really see what's going on there, but yeah, great talk.
I can't actually hear you though. I'm trying to change it. Sorry, maybe I can hear you
Okay,
now.
can you hear me now?
Yeah, I can hear you now.
Okay. I guess very nice talk, and it would have been okay if you overlapped a few slides from when I hosted you, but for your part on ligand binding, predicting whether a molecule will bind and where it would bind, of
Yeah.
course that depends on what the metal is, right? So if you had an ether pendant and you have a high oxidation state metal, it'll coordinate, but if it's low, it wouldn't. Sulfoxides, of course, binding to S versus O is a classic case. Did I miss that you are taking into account what the metal was?
So we can't because there's not enough data. So the first model requires that all instances that are in crystal structures, which is obviously a bias, only have the one pose. And then the hemilability, again, is agnostic, but it's predicting multiple possible poses, but with no awareness of is that hemilability dictated in part because of certain metals. Now, we are looking at reinforcement learning to try to predict for specific metals, what are the competition between different ligands, and there we're using energetics from DFT to try to incorporate that. That was what I was trying to hint at as like the next thing we have to do next.
Yep. Yeah.
Yeah.
Okay, thanks.
Yeah.
Similar note, sorry.
I think your group is here.
Hi, John. Hey,
I
John.
know a certain number of people are there.
Similar note, and also
I hurt my knee skiing,
Yeah.
so I'm pretty slow to walk, and I got to be back for a meeting right now.
Yeah.
So, but
it depends on the other ligands.
Yeah, that's
So,
like a reinforcement
Okay, I was
learning.
gonna know if you could co-train with
Yeah.
ligands.
Yeah, it's just, it's like largely an issue of the data, like even the number of instances you have of a ligand where you know the multiple poses, but I'm very aware, like, you know, on one side of the group, we study iron oxos all the time, but you're never going to see an iron oxo in the CSD. So I even from
Yeah.
perspective know that there's a certain dearth of certain types of
Could you
motifs.
create a
One or two.
Yeah. Could you do a DFT data set to do that? You have a bunch of ligands binding to the metal, you look at comparative energies at different binding modes.
Yeah, so we've worked on that, and that's what we're trying to do a little with our the issue that we run into is that there's competition with solvent, and like even if you do it all at the implicit solvent level, and then when you could have solvent coordinate the metal, and we also don't really believe the DFT energies.
Yeah.
So we've you know, DFT ligand dissociated energies are not something we've historically trusted that much as being, and there are other people who've written on this, like whether like a DFT ligand dissociation energy matches what you see when you in an experiment dissociate a ligand, even in the gas phase. They don't necessarily line up because of reorganization effects.
It's not enough to even just have like a yes or no answer.
I think that's what we're gonna try to do with the RL. Yeah.
Because like I actually just used pidentate the other
Okay.
day for a big set of rhodium
Okay.
with PN. Is it rhodium or iridium PN ligands? And
Okay.
I found it actually did quite a good job across a couple thousand different ligands.
Oh yeah.
Ads.
Yeah.
I was really impressed.
We did for the paper, for the most simplified
Yeah,
paper.
so you guys did iridium.
Yeah, we did iridium just because there's like an interest in the lab in iridium, but we did want to like be like, okay, where we know the ground truth, can it do okay? And it does pretty good.
Yeah. I actually had a question. I started using most of like, you know, it's been fantastic. Have you guys thought about, especially now with the new routine to, you know, kind of sample positions for when you bind on a new ligand to it, any ways of actually controlling like the re versus C phase, like an olefin being bound? Because that's, I realized.
Just put in a bug request and we'll put it, like,
yeah.
we're not very good chemists, so like, I have.
I've been sitting trying to figure out how I would implement it.
Yeah.
Kind of hard.
I have one postdoc, like I usually have one physical organic postdoc who usually has really good chemical intuition and can tell me.
I think I'm the person who writes the most
Okay.
feature requests
Okay.
on Multiply anyways,
Yeah.
because it would be a lovely feature for
Okay,
like
yeah.
asymmetric tals.
Okay, yeah.
Face.
Yeah, I'll talk to Beck about that, and Roland's the main one who's doing
Yeah,
the structure.
I was talking a little bit
Okay.
about
Okay, yeah.
Another great talk. I try not to just pester all questions for like an hour, but I think one I was curious about is, like you said, a lot of the failure modes are kind of reasonable. And one thing that caught my eye in particular was carboxylates.
Yeah.
And if you just look at carboxylates, what's your accuracy rate?
We haven't looked at that, but I did want to say we're trying to do something a lot harder, which is try to predict when ligands are going to favor multinuclear complexes.
Ooh, that's cool.
Yeah, and that's been a lot harder so far, but that's and we run into that, like, because carboxylates could be bridging or they could be on just a single metal bidentate.
Compensating for like
Yeah.
symmetry. If the two atoms are equivalent in the molecule and it predicts one, is that an okay answer for?
I think for carboxylates, we have an explicit fix that we use in the accuracy metric. But
Sorry, can I ask a question about the actual computational part?
Uh-huh.
So I guess
John, you don't have to say, it's just.
Yeah, that was interesting to hear the discussion. Thanks very much for coming. It was great to see your talk. Yeah.
Sorry, you mentioned one of the most frequently asked questions is the accuracy of DFT, but I was trying to ask a different question about the accuracy of the computational model. I guess usually, you know, quantum chemistry calculations don't consider relativistic corrections or spin orbit coupling, but for open shell cases like transition metals, maybe those are actually very important.
We do incorporate them for 4D and 5D, but not 3D, because it's sort of a dominant effect of 4D and 5D. But we have some data sets there, and like generally for 3D, the issue is spin. For 4D and 5D, for sure, relativistic. Yeah.